Before we start, a few announcements. The last seminar is going to be next Wednesday. It's going to be Habib Nazm from Sandia National Labs. And on Thursday, we have the spring social event for CICS. If you are interested to attend and students are invited, you need to email us so you're on the list. Okay? So it's going to be 5 to 8 o'clock next Thursday. So faculty should invite their students to attend seminars. If you don't attend seminars, don't invite your friends basically who don't come. Okay, we don't want them, even though we have free food. All right, it's exciting to have Professor Chen from Northwestern University. She's very regular at Notre Dame. She was here 2-3 years ago as well, and she will be back, I'm sure, within a year or two again. And I am not, she asked me not to read all her biography, which was a mistake, because on the last line, I realized she just became a member of the National Academy of Engineering in the class of 2019. And missing that would have been an embarrassment on my side. So, congratulations.
Thank you very much.
And everything else is also, it's secondary at this point in your career. So we're very pleased to hear a talk on multiscale, multidimensional uncertainty quantification in integrated computational materials engineering.
Thank you very much. And I'm very extremely honored to be part of the National Academy of Engineering. Here we have some senior members also sitting in the audience. And thank you very much for coming to this talk. I know you have talks every week, so I hope it's not too overwhelming for you. And the subject I want to discuss today actually is kind of technical, I feel. I have to sometimes read the paper a couple of times, try to remember every details of this work. It's a very complex topic. How do we do uncertainty quantification for multi-scale and also very high dimensional problem? And in this new paradigm called ICME, that you might heard about, is integrated computational materials engineering. So this effort is a joint effort between my group and a couple other labs at Northwestern University. So that includes Professor Jen Chow's manufacturing lab, Professor Wing Kan-Liu's mechanics lab, and also a couple other faculties are involved. And some of the slides are actually taken from them. I want to give a very quick introduction of my group. It's called IDEAL. So we currently have couple postdoc, majority of them are PhD students. And we're in general interested in methods for support engineering design. So even though many people are working in the UQ area, but from the engineering design perspective, the goal is really try to design product that can be more robust and more reliable. So we're developing methods both optimization-based as well as statistical-based. So in my early career, I've been working mostly on algorithms for design under uncertainty. So if you look at my Google Scholar, most of the highly cited paper right now are actually in my early career of say design under uncertainty, like design for robustness, design for reliability. In recent years, this topic, a lot of the methods have become very mature. So I've been working on mostly model uncertainty quantification. So that means when we have both computer simulation as well as physical data, how do we combine them together to quantify the model uncertainty? And one of the use case for those methods are very large scale, we call MDO, multidisciplinary design optimization. So many of the cases I worked on in the early part of my career are automobile, aircraft, those kind of examples. But in recent years, I found lots of opportunity of applying the design methods in the field of materials. So today I'm going to focus mainly on the one that in the middle, which is called the design of emerging material systems. And most of those systems are at a very lower scale level, like a nano scale level. But we're also working on method for topology optimization for metamaterial design, as well as on the right, this subject of enterprise-driven decision-based design is a very different subject, looking at human behavior or consumer's choice behavior engineering design. So we're using network analysis-based approach to support engineering design decisions. So today I'm going to mainly focus on what's in the middle, which is design of emerging material systems. So in recent years, a lot of funding opportunity arise related to this material or ICME called. The basic idea is really to integrate data science together with materials modeling, very physics-based, and also manufacturing relations. And to design, and very importantly, not just a material, to design new material, but also how you deploy those material into product and a device. And there's many usage. The reason there's a lot of opportunity in this area is because there's many wide applications of advanced material systems. But from my experience so far, I found that it's a very difficult subject. And one of the reasons, it's very interdisciplinary. Just working with my mechanics colleagues and manufacturing experts, you realize that there's a lot of issues, there's a lot of barrier here to integrate all these things together. So the need to handle this kind of interdisciplinary challenge is also kind of evident in a new a term you probably heard about called the Material Genome Initiative, right? So this, you probably won't be able to see this very clearly. So what is showing here, the MGI, the goal is really try to integrate computational tools together with experimental tools as well as the digital data. And it's interesting to note that they play a different role in this process. You can think about that the experimental tool or data is try to bridge the gap between lack of knowledge when you're using a computer model, right? Because when you build a computer model, there's always something that you're not able to capture correctly. So the experimental tools play the role, really try to bridge that gap, lack of knowledge gap. So what is the role of digital data play? Or we call the data science, right? Data science actually is playing an important role when we have actually the lack of computing power, okay? Even when we have a good model, we may not be able to simulate everything, especially when we consider uncertainty. So that's where the data science play, and that's where a lot of the research opportunity arise. I know that many of the audience here are also working on data science methods, right? Try to bridge all these things together. So most of my colleagues, if you look at this lower part, this figure, most of my colleagues, they're working on creating relationship between processing, like manufacturing or material processing, to structure. It could be large part or could be microstructure. And some of them are doing mechanics modeling to predict the structure to property behavior. And there's also a difference between property and the performance. So when we talk about performance, that's usually associated with a part. When we talk about the material property, that's usually just a single point. And that actually leads to a lot of challenge in the analysis process from property to performance. Oftentimes they increase the significant amount of the computing requirement. So my group is actually working the other way. We're design groups, so we're looking at the problem inversely, so giving us a target of performance. How do we quickly explore the design space for the structure, for the process? So we can do concurrent material design, structure design, as well as processing design. So that is the kind of the big problem we try to solve. But today, I'm not going to talk much about how do we do that. Today, I'm going to focus mainly on how do we incorporate uncertainty in this process when we assess the uncertainty on the property and on the performance. How do we do that? And what are some of the challenges associated with that? And the type of uncertainty I want to focus on mainly related to structure. Okay, there could be a lot of uncertainty, like the loads and those things. And I want to use this example. It's a project related to lightweight structure design using carbon fiber reinforced composite. This project is sponsored by DOE, and the main a company that leads this effort is Ford. So Northwestern has been working with Ford very closely for the past 4 years. So this project has been just completed. And so it's a multi-scale problem that if you think about it at each different scale level, the lowest picture shows like microstructure with fiber. So there's a matrix, is epoxy. So there's a design problem associated with what kind of epoxy you use. And I have a colleague here who does molecular dynamic simulation. And going one level up, you're talking about design decision can be made for the laminate. So there's architecture design in terms of the angle, how many layers, things like that. And going up, that's the component design. So that usually is related to topology of a structure, right? So in the past, traditionally, mechanical engineer only works in this macro scale, the highest level, and we assume the material is the same everywhere, okay? But in the reality, they're very different. And one major source of the difference or the variation is actually caused by manufacturing. Because if you think about a part has a shape, and after you apply the manufacturing processing condition, and at each different location, the structure can be very different. For example, the fiber angle is different at the different location after you do the preforming. So how do you take into those account of variation? And if you look at the small scale level, those are the image that actually taken by Ford that shows that the fiber shape can be different. They're usually not round shape, and that could lead to actually damage behavior. The lower part shows the distribution, the stress distribution for circular versus beam type of shape. You can see that with beam type, it's more prone to damage. And the fiber, there's thousands of fiber if you take out a single point, and there's a misalignment issue. So there's literature discussing about the misalignment could lead to a large, it could lead to damage behavior at the end. So how do we take into account this kind of variation? That's the subject that I want to kind of discuss today and show you some of the methods. So when we start to take into account the variation, we're talking about that the constituted relationship is going to be stochastic. So what is constituted relationship? If you're not working in the material area, you can think about it's just like a government has a constitution, right? The constitution relationship determines the material behavior. It could be like a linear elastic behavior and all the way to nonlinear plastic behavior. So there's a stress and a strain curve that is showing here. Now I show a bunch of curve means there's stochasticity there. But in general, stress-strain relationship represent a constituted relationship of the material behavior. So this is actually a critical link between different scale level. So I'm going to show you how do we build model, stochastic constituted relationship model to take into account the microstructural variation, and then all the way up to the highest level scale impact. So in this process, we have considered many different composites like unidimensional, SMC woven. The woven is the most complicated one that you have different woven together, right? They're kind of tangled together. And in each of this case, you can see there's different source of variation. The non-uniform distribution represent the volume fraction can be very different at the different locations. So all this fiber have this issue. And then if you have the UD composite, you also have the fiber waveness that can introduce like a large deviation in the performance, and also the fiber misalignment. So waveness and the misalignment are two different concepts. Okay? A fiber can be waved. That misalignment means that how it deviates from the perfect location. So the perfect location can be waved, but then deviation from there, it's called the fiber misalignment. I think I have a picture later on to show the misalignment situation. So we want to understand the relative importance of all these different variations to understand their impact on the part. Really, we're talking about at each different location, the property is different due to the structure variations. So we want to create, our solution actually is create a kind of a surrogate or meta model-based database so that we can say for any given structure, this is going to be the property. Okay? And also this meta model takes into account the spatial variation. So that's quite different from the traditional kind of deterministic meta model. We like to take into account the structural variation, the impact of the structural variation in this model. So, and another case, this is another motivating case to kind of explain why it's so important to consider the microstructure variation from one location to another. So that's an additive manufacturing process that my colleague Greg Wagner, his group has developing the simulation codes that actually starts the 3 sets of simulation, start from the 2-pass generation to the melt pool, very much fluid dynamics based, and at the end to the microstructure that at each different location. So what you see here, the picture is actually the grain structure at the different locations. So those kind of simulation is very expensive, and there's a need to kind of build a model that can quickly assess the behavior at different locations. And this microstructure variation can be spatially coupled, as well as that there are also another type of structure that we need to consider is called the defects. Okay, so there's microstructure which relate to your material, so that's related to material design decision, but there's also there are defects that you have to take into account when you think about the property. So in general, this shows it's also a function of time. You can see that the volume fraction at each different location at a different time, it's also kind of has variation. So it's different quantity shows the temporal variation as well as the spatial variation. So it's high dimensional because of this reason. Temporally, spatially, there's variation, but they're very highly coupled. So the 3 sets of methods that I will discuss today, there's 3 sets of methods that are related in order to address this kind of uncertainty. The first one is that we need a method to characterize the microstructure as well as to do reconstruction that can digitally reproduce those inputs as simulation, as input to the final element simulations. So that's one category of work. The second category is given the microstructure variation, how do we do uncertainty propagation throughout the different multi-scale levels? So it's a very daunting problem, requires a lot of computing power. So how do we manage that kind of complexity? The last subject I want to discuss is all the model we have is not accurate. So we have experimental data. How do we use them in the context of multi-scale simulation, and then try to improve our model so at the end they will have better predictions? So 3 subjects, they kind of interrelated. So the first subject, I'm going to just talk very briefly. We have a review paper published in Progress in Material Science last year that reviewed 4 or 5 different type of methods. So it kind of also shows the progressing of my group from one method to another. The upper picture just try to point it out is that depending on the window size of your RBE, that's called the representative volume element, your uncertainty, the impact of uncertainty can be quite different. So if you choose a very large window size, for a linear behavior, there's almost no uncertainty. But for the plastic behavior, you see a little bit uncertainty there. But for some other very nonlinear behavior, like a buckling and some other plasticity behavior, you can see that the window size has a huge impact. So using the SVE, this is called SVE, oftentimes is due to the lack of computing power. So in order to count for the uncertainty, we had to do multiple realization so that we can really look at the impact of the lacking of computing power. So that's the reason we created this method called the reconstruction to try to reproduce statistically equivalent microstructure that we can see what's their impact on the property uncertainty. So the most original method, there's a person called Takota at Princeton. He wrote a book and he also has papers on this method called the correlation function. So it used statistical function and to fully represent the microstructure morphology. And this kind of method, the reconstruction is very expensive. It's using optimization-based approach. Basically, start with like randomly place the particles and then try to make them optimized so the correlation function match with the target correlation. So it's very expensive. You cannot really use it at all in the design process. So for the design purpose, we actually propose a descriptor-based method. The descriptor have some assumption of the shape of the particle, could be like a ellipsoid, right? And then you use certain parameter to represent the particle size, geometry, the dispersion status, and then some other quantity that is important. This method is very fast. But on the other hand, it cannot model very like irregular geometry. So for the irregular geometry, we actually developed two methods. One is model-based, based on supervised learning. So basically put a small window, scatter through the whole image, and try to build a machine learning model to predict 0 or 1 at a particular location. And using that model for reconstruction is very fast because it's a model-based approach. It's not good for design because it doesn't really give you very explicit variables. And then in recent years, we looked at neural network approach. There's two cases. First, we use it for reconstruction. For that, we only need one image and use the transfer learning idea using an existing library that's called the VGG19. You probably heard about that trend based on the animal geometry, actually very powerful for material. You can also use this for reconstruction. So for one image, we can reconstruct a statistically equivalent image using this network. We also extended this one. Last year's paper was on using GAN, like the generative network, to do material design. So we could actually design material by just using the images rather than the parameters. Okay, so that is, I think many of you are familiar with the GAN idea, is to build a model using some training data and then try to use it to create optimal solution for the latent variable, right? And the latent variable can transfer back to an image. And another approach is we call the physics-aware method, is actually a spectral density function method. We found it very useful in like a solar cell design problem, battery design problem, is because many of the material structure, after we transfer them to the Fourier spectrum, you can see that the structure, the dimension that used to represent the structure is very small. So in this case, you can see that on the left, it's a very complex quasi-random. We call this quasi-random structure. It's random, but there's a pattern underneath it. So after you do the Fourier transformation, you can see that you only need the two parameters, the lower and the upper value to represent this function called SDF. This happens to be a step function, but there are other cases with different functions. So what we do right now in material design, we actually, from the existing images from a particular process, we generalize what is the underlying spectral density function. And then we use the parameter in the spectral density function as a design variable to do design. And that also allows us to do a quick map to the processing condition. And oftentimes we can create very good map because there's a physics meaning behind it, although spectral density behavior, it's related to the dispersion, to the size, the geometry, local size, local geometry. So we're testing this method on many different material systems that, so I have some collaborators in the material area that I work with on this kind of a design. Usually it's for optical system and also for nano-composite structure. It's a very powerful method. So, and for the fiber problem, we actually find that it's not an easy problem when we think about those waveness and also the variation of the like the misalignment issue. And I'm showing a lot of picture here that it may be difficult to understand each of them. But what I want to say here is that actually this is a work where the engineering comes in, that basically we have to work with the existing images. So some of the real image I'm showing here, like this is a real image, this is a real image, and this is a real image, that there's a lot of practical issue. For example, the image usually, the resolution is not good and leads to a lot of kind of lines that are disconnected, right? But in reality, they're connected. And the regular kind of a well-behaved uncertainty model doesn't fit for this kind of variation. So my students, this is more like a problem-solving cases that we're identifying the best model that can kind of quantify the uncertainty. So those models involve tree structure, the non-homogeneous Poisson process. Here, for dealing with the imaging quality, we're using segmented linear regression to identify the wavelength pattern and the frequency associated with that. So a lot of engineering work in order to really count for the uncertainty based on the image. Okay? But most of the work actually starts from image. And on the right, you can see some packing algorithm we developed for packing the beam. Actually, it's not a trivial task if you want a very high volume fraction. It's optimization problem. And also packing the chips for this SMC sheet molding compound, we're using a volume diagram-based approach. So this idea we borrow from other fields and try to serve the purpose we want is really try to generate, we call the statistically equivalent structure that match with the imaging data that we got. So let's say we have those data, right? Let's say we have those images, we have those models. Now, how do we take those things into account when we assess their impact on the property? So this paper has been published also last year in the CMAME that has a lot of description on that. But I want to just highlight a couple of things to understand really the key idea behind it. Today I have been discussing a lot with some of you on the PDE-based kind of problem, right? So in the finite element-based analysis in this case, there's a PDE governing equation, but on the other hand, our analysis is very much black box based, okay? Because you discretize each point, like a window, you call them integration point. But there is an important relationship between different scale. Basically, the stress information passed up and the strain passed down. And this is considered as basically called a constitutive relationship. So that's a key idea in our work is we do microstructure based analysis, but the information passing from one scale level to another relies on the constitutive relationship as well as the uncertainty quantification associated with that. So the challenge here is really the cost, right? If you want to consider the detailed microstructure at each different scale level, I will show you later on what is the degree of dimensionality that's involved. There's very high dimensional, very computational cost. One of my colleagues, Wing-Kan Liu, actually is developing method to try to reduce that cost for this multi-scale analysis. Another really challenge is that that those uncertainty are spatially correlated because of the manufacturing process. Okay, so there's some kind of physical constraint determined how these structures are different at different locations, and they're also coupled throughout the different scale level. So when we thinking about uncertainty analysis at different scale level, we have to make sure those structure information we give needs to be compatible. So we are developing a method to try to making sure that is taken care of. So the kind of uncertainty I'm showing next involved, this is a double dome structure after preforming. You can see the angles are different. This is the Young angle are different at different location due to the manufacturing process. Here is an example of fiber misalignment. So you can see that the fiber kind of deviates from its ideal location and it leads to misalignment that will introduce a possibility of damaging behavior. And this misalignment is described by two different angles, theta and the phi, that is reference to the ideal location. So this is the deviation. The angle shows how much it deviates. So those are the random, you can think about those are random variable like theta, phi, as well as alpha. Those are the random variable in our problem, but they have coupling between them, okay? So just illustrating why this is very computationally expensive, imagine that you have a specimen. Right now we're just using a symbol like coupon kind of, our test, actual physical test is also at this kind of coupon level, okay? So we have physical data related to that. The color represents volume fraction at different locations. So on average, they're 55% volume fraction, but the color shows the volume fraction is different at different locations. And the integration point here is 15,000 integration point. So if you amplify one integration point, now it becomes an RBE at the mesoscale level. And this woven composite have 4x4 kind of, we call each of them like a tall, right? And then 4x4 together. And this 4x4, even if you do multiple realization, this particular point may be the average volume fraction is 62%. And this color shows the variation of the volume fraction. And they can be quite different. This is just one realization of uncertainty or variation. This is another realization. And you can see that the volume fraction vary from one location to another. It could be anywhere from 50% to 70%. Okay? And if you do one more expansion, that will be the microscale level simulation. And now you can see each point, that's a cross section. You can see thousands of fibers, okay, basically there. And those fiber has angle, has misalignment that you have to take into account. And this different realization, you can see that their volume fraction is also different. So I'm just using one example of random variable volume fraction, but in our problem, we actually have the misalignment angle, two angles that we take into account. And they are coupled. There's some coupling between them with the volume fractions. So if you multiply, this is a nested situation, okay? So 15,000 K, this is 640 K integration point, and this 5.4 million integration point together. So it's a very large amount of work if you want to do all of them like simultaneously using the original simulation code. So in the prior work, we always just saw people just treat them as a random variable, like volume fraction is a random variable. That doesn't really solve the problem, because if you're thinking about a random variable, everywhere it's the same for a particular sample, okay, they take. So that would be just multiple realization of different volume fraction, but everywhere the spatial variation is not considered at all. So we want to consider the spatial as well as part-to-part variation, and we want to develop a method which is non-intrusive, so that can take finite element as a black box. So the method we use to quantify uncertainty is actually just a multi-response Gaussian random process. And I think many of you may be very familiar with this concept. This Gaussian random process, now I just show them as single spatial variable, just one dimension, okay, not in 3D, just x1. It shows at different location, there's a different volume fraction, there's a mean, the omega kind of shows how strongly from one location to another they're coupled as a mean value, and there's a variance. So when you have two quantity, like volume fraction and one of the angle deviation, now you see that there's a coupling, right? And the coupling is taken care of by this matrix here. So on the diagonal shows the variation of the individual quantity, each random variable. Off diagonal shows the correlation. So in this case, it's negatively correlated. It actually has physical meaning behind it, like the volume fraction increases and the misalignment angle usually decreases. Okay, so this kind of coupling has some physical interpretation behind them. But in general, we're using a Gaussian multi-response Gaussian random process, and we are using this nested, we call a spatial random process to capture the coupling between different scale level. Okay, so how does that work? Let me show you some more details. So at the macro scale level, we create a spatial random process to simulate the structural variation, okay, for those 3 parameters. So they go through the microscale simulation. At the mesoscale level, we also create lots of samples, right? For the mesoscale, that's the RVE level simulation. And then it also gives us the behavior called the mesoscale simulator. And the most important thing is the coupling between them. So one coupling is that for the structural variation, we're using top-down sampling. So the hyperparameter in the upper scale level become the response of the SRP at the lower scale level. Okay, so that's how they are coupled together. And then another coupling, it's one way, is that the mesoscale simulation, considering the mesoscale structure variation, will give us a surrogate model of the constituted relationship at this scale level, at this mesoscale. And this constituted relationship will be passed to the microscale level to do macroscale simulation. So at this scale level simulation, instead of coupling 2 FEM together, right now I'm going to feed a surrogate model at this scale level to the macroscale, so that at each different point, it will just say, what is the structure, right? What is the inputs, like the microstructure definition, and then it will tell me what is the property. And so this surrogate model, it's still based on homogenization, so that's one assumption you have to keep in mind. And we're working on a problem that actually does really homogenization may break down, and how do you do that, right? So for this linear behavior I'm showing here, we're using a homogenization assumption that the RVE at the lower scale level will create constitutive relationship meta model that pass to the upper scale level. And the same thing happens in the coupling between meso and the microscale level. So there's also top-down sampling and then the feedback homogenization. And in this process, we also used two approach. One approach I already mentioned about is meta modeling. So again, I call them engineering approach, right? Where we have very large complexity, how do we manage it? So one is meta model, but different from the traditional meta model, our inputs here could be statistical quantity, like could be something related to the macrostructure variations, the statistical parameter, rather than like a deterministic kind of parameter. Another thing we did is really engineering approach is sensitivity analysis. We actually did a lot of pre-screening tests, try to figure out what are the important variation source, and then try to use them to reduce the complexity. So this slide just basically shows how we do the coupling, or we call it top-down sampling. So just like analogy is that a Google map, right? When you look at the macro scale and you try to make sure when you zoom in, things match up with the top level. And in the statistical sense, it's more difficult to accomplish. But we accomplish that by a nested SRP model. So the hyperparameter, it's for the highest scale level, become the response of the multi-response GP model at the lower scale level. So the number of hyperparameter can increase, from one scale level to another. And how do we deal with, like, some people may question about how general is random, like a Gaussian random process, right? So Gaussian random process could be actually handle very non-normal distribution, right? You can actually transfer if it's a marginal distribution. If it doesn't follow normal distribution, you could actually use transformation to make them normal. And if you think about how this is chained together, at the lower scale level, actually the random field becomes non-stationary. Even though the upper scale level, the GP model is stationary, but if you think about after you do this cascading, and at the lower scale level, it's really very non-stationary. So this is basically the model we use. You could use some other method like Coppola, polynomial chaos function, and those things. But there's a good reason that we use GP model, because it's flexible and it's the most simplistic model that we think can represent the random field and also allow us to quantify the uncertainty. So let's talk a little bit more about the meta model we built. So exactly what is the meta model? So constitutive relationship is described by stiffness matrix, right? I think people here probably know about the Hooke's law, right? Hooke's law has the K as the stiffness parameter, but in a very complex structure, it is not a single variable. It is actually maximum, I think, can have 36 elements, okay, in this matrix for a very complex structure. So for this woven composite material, at this scale level, the mesoscale level, we are using about, I think here is about 20, but some of them are symmetric. So there's some kind of symmetric property. So it's less than 20 variable. And those are the response, basically, in our surrogate model. And what we try to fit is this variable as a function of the material property, as well as the statistical description of the microstructure that we're interested in. And this statistical description take into account, we call them uncertainty source, take into account the coupling and the variation in the system. And so that basically become an emulator in our problem. And the one nice thing about GP model is it can quantify the uncertainty. It could also allow you to determine where you should pick more samples, right? Because we always have a case that we do not have enough samples. So we have to decide how do we do this sequentially. So this one that based on a certain amount of sample, we could actually show that 95 confidence interval for C11 as a function of the average fiber volume fraction as well as the Young angle. Okay, so here is one example of statistical quantity. We could also use the variance of the volume fraction as an input to take care of the statistical quantity. So sensitivity analysis, we're using the Sobel sensitivity analysis. So this just shows that for all those elements, C11 to, here we listed about a dozen C elements here, we can look at what's the impact of the different variable on those parameters. So in this case, we actually shows like the fiber Young angle is the red one is always the most significant, and the next one is the matrix Young's modular for the matrix property, and then the volume average volume fraction is the yellow one, is also quite critical. But we also find things like the theta, which is the misalignment angle, the green one, is not so critical for this kind of behavior we're interested in. So we're interested in this case is a linear elastic behavior. Okay, we're applying the load in different direction and try to look at the constitutive relationship. So this kind of exercise was done ahead of time, or as the first step, allow us to decide what are the variables that include in the model. So here is just some details about microscale level. We have a surrogate model to represent the constitutive relationship. So for that stiffness matrix, the number of elements is slightly less than for the mesoscale. We have more elements. And this curve here just to show you what's the impact of the training sample on the error of different models. So you can see that, for this kind of a training, for the microscale level, actually like 80 samples is quite sufficient. And for this is the mesoscale level, 60 samples is quite sufficient, okay, for this kind of a behavior that we're interested in. So once those surrogate models are built, those information are passed to the higher scale level to look at this globe. We call the impact on the global behavior, or the macroscale level. So in the material behavior, it is really the relationship between the force as well as the displacement. Okay, so that's this curve here shows when you have no uncertainty. Okay, that's the blue curve, and the red curve shows the mean when you consider uncertainty, and the dashed line shows 90% confidence interval. So you can see that. The behavior, when you consider the uncertainty, you can see there's more higher stress level or distribution. So this is no uncertainty. That's how the stress profile. And this is when you consider the uncertainty, that's the mean. So the mean profile is still very close to when you have no uncertainty. But that's the standard, basically the standard deviation of the stress level. So that's really the impact on uncertainty. We only looked at 2 moments, the mean and the variance. And you can see that when you take into account the uncertainty, they're indeed introduced more stress concentration at certain levels. So the next step for us is really try to take into account more nonlinear plastic behavior, as well as like defects when you think about introducing voids at different locations, right? And how do you do sampling? It becomes tricky. And also when you're thinking about higher, like a nonlinear behavior, the constitutive relationship is also path dependent. That you have to take into account the past, so it's become more dynamic. So some dynamic modeling technique needs to take into account. So just a kind of summary of what I just talked about this subject. Basically, we just develop a method which is a non-intrusive approach that take a finite element as a black box at each scale level and account for a multi-response and a non-stationary uncertainty source. It also allows to assess the multi-scale effects from the micro, meso, all the way to the macro. And the physical insights gained basically are related to the hyperparameter in the GP model, because GP model gave you some insights of the behavior compared to some other methods like neural network. And impact would be more critical. We expect to be more critical. The example I show you, 16% variation is not big, but when you think about nonlinear behavior, it can be quite catastrophic, at certain locations. So the last subject is also related to, I want to discuss a little bit about this topic of a model uncertainty quantification, and how do we do that in this multi-scale context. So this paper is published also last year, Composite Science and Technology. So we are looking at how do we use the data. This model is a manufacturing model. So it's a manufacturing process model really to simulate, given the manufacturing process condition, how the temperature and those things, how the structure varied from one location to another. So this is a thermal related process. It's a very flexible process to form the shape into different shape that you want. But on the other hand, it's also very nonlinear because it involves plasticity. So in the past, most of the model does not consider the so-called tension shear coupling. They only consider the tension, but not with the coupling with the shear. And they use least square method mostly to calibrate their model, okay, and just to fit so parameter. So what parameter they calibrate? In this case, the model is a finite element simulator at the mesoscale, and the parameter you calibrate related to the Young's modular, okay, and also this is the shear. This coefficient here is related to the shear, and then the inputs here are relates the strain and also the shear angle. So gamma is the shear angle, and the epsilon here, 1, and 2 represent the effective shear. It's a normalized number along the WAP and the weft direction. When you talk about composite, right, there's two critical directions, WAP and the weft. So there's a prime there. And then the output is the stress level, like sigma 11, sigma 22, and sigma 12. Okay? So those parameters are kind of unknown, difficult to measure. So we want to infer what could be the parameter. So the approach we're using is called the Bayesian calibration and also validation. And we differentiate the two because calibration is to use data to try to infer the unknown model parameter, but validation is use new points that you didn't use in your calibration, try to see how good is the calibration. And this model, calibrated model, basically it becomes an emulator. And we also did validation using this emulator at the macroscale level, try to see how good is the predictive capability. So there's certain things we try to assess how good is this calibrated model. So the test data we have actually is very limited. We have the data we used in calibration only involves the data from uniaxial tension test. That means your shear angle is 0. Basically, you pull the specimen in one particular direction, and you look at how the sigma 11, the stress change as a function of different strain level. Okay, so that is a curve that you record. We also collected some very limited data, taking into account the shear behavior. That is the bias extension. So you can see now I marked the weft and the WAF, there's two directions there. With that, we have some more data on how when the shear angle change, how this behavior is different. We actually reserved this data for validation. Okay, we didn't use this data, the shear angle, even though that's a model input, gamma 12 is input of a model. We didn't use that data at all. We used this to validate how good is the calibrated model. So this approach we're using is, some people probably know the Kennedy-O'Higgins approach, right? And basically says that the prediction, the experimental data, is equal to the model prediction plus some bias function and plus some physical experimental error. So the unknown here has both the theta as well as the bias function. So the bias function tries to capture the method error. So that's the difference between our work and some other work a lot of the work, existing work for model calibration, they take away this delta, they only look at theta and they try to lump all the uncertainty into theta. And we try to put them as a separate quantity to quantify uncertainty. And in this process, we use a modular Bayesian approach. So first we build a surrogate model for our computer simulation, and then we also build another surrogate GP model for the bias, okay? And that one has very limited physical data, and for that reason, the GP model actually plays an important role because it quantifies the uncertainty associated with lack of physical data. I'm going to skip the detail here, but just to walk you through the step. The first step is to build the constitutive relationship just to use the computer model simulation. And then that's a function of the sigma is a function of the theta as well as the input x. And in this process, we also used some physics-based knowledge to put some constraints on how the stress and the strain may change at the corner, like very nonlinear kind of behavior. So if you do not put constraints, that's what you get. But the physics-informed one give you more accurate kind of a prediction. And the module 2 is to to first identify the posterior for the calibration variable, and that is using basically the conditional probability and doing lots of random simulations. So you can see that the prior, we just assign some uniform distribution, unknown parameter based on experiments for those Young's modulus, and then you can see this is the posterior after taking into account the physical experiments. So there's still uncertainty. The data we use is only the unit axial tension test data. And those quantity is measured for the specimen. So then this tells us, how much uncertainty that we have. But in general, they're pretty much identifiable. In some of other research, we actually talk about how do we deal with non-identifiability. So then we did the posterior on the whole function, which means we start to quantify the uncertainty of the bias function. So you can see that the bias function actually, the increases, in this case, the stress level increase when the epsilon goes up, the bias goes higher, okay? And this also shows you when the shear angle increase, that actually this bias, this two quantity, the bias goes lower. So the validation is the interesting part is the part now we used the biaxial test data. So that's when the gamma is not equal to 0 anymore. So you can see that there's still some variation of the prediction after you did the model updating, but in general, it's quite acceptable, that kind of uncertainty. So this is an example which tells us that actually it's kind of interesting to use uniaxial in two directions, okay? This way and that way. Try to predict a behavior that has a shear angle that you do not have data, and it shows us that the uncertainty in this case is still tolerable, okay? And now we use it for the global validation, which is for the whole structure. That is that we're looking at the impact on this big piece, right? So we looked at this, actually it shows the experiment data. It's a green curve, so it's kind of fluctuating. And the decoupled model is what people used in the literature, does not consider tensor and shear coupling. And the red curve is our calibrated multiscale model. So you can see that at the highest scale level, using the corrected material behavior, calibrated material behavior, we could actually predict very well the global behavior for the whole part. And this also has some more detail here, shows the angle prediction at different locations. That's the output of our model. You can see that for the decoupled model, that's what's in the literature, and the multiscale model is from our prediction, and the experiments is the true data. Okay, so you can see that our prediction gets closer, much closer to the true data compared to the decoupled model for the angle prediction. So that's just an example to show how we do multiscale modeling. So I like to kind of summarize that what we have discussed today, that I have showed 3 different subjects. They are kind of interrelated. One is that in order to quantify the uncertainty of the impact of a microstructure, we have to first work on methods that can help us to characterize and also reconstruct the microstructure. And we need multiscale evaluation that is efficient, fast, that allow us to assess those impact of the lower scale behavior. And the Bayesian validation and calibration can play an important role when we have some physical data that we want to introduce. And in general, the takeaway is that first, a multiscale material system is very, very complex. If you think about it, it's very difficult to decouple them. So in the design area, we actually have a lot of ways to manage uncertainty that try to decouple things into subsystem. There's really no subsystem here. Everything is related to everything else. So it's very complex. But the stochasticity can really play a critical role. That's where the uncertainty methods can really make a huge impact on taking into account the stochasticity. And the linear or nonlinear dimension reduction can help to significantly speed up the process. And by nature, design and the manufacturing are very highly coupled. So I think for a material scientist, they probably do not think too much about manufacturing yet. But as a mechanical engineer, we always have the need to deploy the material into parts into a system. So the manufacturing process impact, which leads to the structure variation, at a different location is very important to consider. And we need the methods which allow us to bridge the gap of these different domains. And this is also an area that I found that both the big data and the lack of data coexist. So in general, this material genome initiative is trying to use big data to answer questions or develop novel material. But in material science, actually, most of the situation we found is lack of data. You have some big data related to the imaging, okay? This is like a terabyte or some kind of very huge number if you store all the image information. But to do new material design, you will find that there's very little data talk about especially composite behavior. Like if you put this material together with another one, what is going to happen, right? This interface behavior needs to be modeled, and the data are very sparse. So how do you consider, you need a method really handle lack of data, which is the reason why I present the Gaussian random process method. It's a very nice GP method. It's a very nice method to take into account of lack of data, which allows us to decide how do we do sampling. So there are various sources of uncertainty that needs to be considered. It's not just the spatially variant, it could be temporal. I haven't talked about the temporal kind of variation, but those are also very important to consider. So finally, I'd like to really acknowledge the funding support from these various of different sources. The project I talked today are mainly sponsored by DOE as well as Ford. But at Northwestern, we have several major initiatives right now going on. One is the CHAMAD is mainly a material genome related activity. We finished the first 5 years, and it's renewed for another 5 years. So we are at the second phase right now. There's different case study that we user case we're looking at, like we try to collect the data and we try to use the data for new material design. And the DMDII is a regional called Digital Manufacturing Design Innovation Institute. It's actually the headquarters is in Chicago that supported many of the work related to additive manufacturing. I didn't go into details of additive manufacturing today at all, but there's some effort there also try to do validation of the model that is developed. So there's many different agents that have contributed to some of the results that I'm sharing here today. So with that, I'd like to see whether there's any questions. I will also send some publication as part of the PDF.
Thank you very much. We have time for a few questions.
Yes.
Can you give examples of temporal uncertainties in this particular case?
Yeah, so the temporal uncertainty is the case that, the need to consider the temporal uncertainty is really this need that you will take into account at the different time how the material is going to behave differently. So the path-dependent constitutive relationship, which is very important for the plasticity behavior, is that you need to really model the function, not necessarily as a time, but you want to look at the new state as a function of the previous state. So that is an example of that, the temporal, and the uncertainty source is coming from the still coming from the microstructure. But you want to capture the impact on the quantity that you're interested that will change as a function of time. So the dynamic, anything which is dynamic behavior would be considered will involve this temporal issue, the high dimensionality issue. Yes, yeah.
Do you think non-stationarity is an important feature for Gaussian processing in the context of material design?
Yeah, so I have talked about that how do we look at, we have different scale level model, right? So at the bottom level, if you're zooming in to the highest resolution, it's totally non-stationary, right? But if you aggregate some property, it becomes the highest level is stationary. So that is assumption we are making in our method. But even if you have non-stationary behavior, you could still use some non-stationary model to handle that. There's also non-stationary GP model that can deal with those kind of situations. So I think it's really problem dependent. Currently we do not have a, I think that we only measured the quantity at the station in the highest level, like volume fraction, as well as fiber angle. So far, the stationality is pretty good. The assumption of stationality is very good at the high scale level.
And do you think if you have, for example, if you have limited data, the net stationarity can be hard to capture? So how do we deal with net stationarity when we have?
Yeah. So quantify the uncertainty is actually a big challenge because you need lots of image, right? From part to part, from location to location. So for our project, we actually, for the lower scale level, we just assumed some parameter because we didn't have the resource to collect all those, images. So I think the image-based approach is an ideal way to do that. But in the case of lack of data, we actually have we looked at the literature, so some other paper published before make some, based on some physical data, they assume some coupling between some variables. So that's also our knowledge base, yeah. But it is a challenge if you say, I want to start from the real data to quantify my uncertainty, yeah. I don't have a good answer to that, but that's just something we sometimes have to just assume based on both the knowledge and just the experience, yeah. Yes?
Yeah, so you said something about non-identifiability of estimating the constitutive relation.
Yes.
So can you say something more about that?
Yes. So the non-identifiability is related to when you have multiple theta in the equation as well as bias function, because it's an inverse problem, right? You match the response. So your inputs, the theta and the bias, could have some different combination that leads to the same response, right? So yeah, so some people say, I don't care those things because I only care about the predictive capability. But in our case, we do care because those theta has some physical meaning, like Young's modulus. We do like to know what is the Young's modulus so we can use it for more high-level system analysis. So the method we have published is to use multi-response data to handle this issue. Like we are collecting, sometimes the data are free. For example, if you collect the stress for a piece of parts, you have information at the different locations. So that is multi-response. And multi-response in time domain could be a multi-response or multi-response totally different quantity of interest. That could also help you to infer the unknown much better. But this is one issue that everybody acknowledges, but not many people really do research on that.
Okay, so you said as increasing the amount of information somehow.
Yes, because it's the unknown is a lot. Yep. Sometimes the calibration variable have a dozen calibration variables. People do not know what's the value, right? So inferring those variables can lead to many different possibilities. Yeah. So you sometimes use your prior. That's another reason you use Bayesian. You kind of try to use the prior to constrain them. Yeah. Question?
I have a question on the top-down sampling method.
Yes.
So, for example, you have a variable at the top level, and so you generate 100 samples for that variable. So that means, in the mesoscale, you need to build 100 circuit models for that, and that would be much more in the micro level. So that's what requires a large data set to build all those circuit models. So I'm thinking that whether you can incorporate all those uncertainties in one circuit model, and so that maybe can reduce the data set.
I understand your point about that this cascading will introduce more response, right? That you need to, actually the more response is not related to the responsiveness model. The dimensionality of responsiveness model is related to the coefficient in the constant relationship matrix. So that size does not change. The only thing changed is the inputs of your model. So the input can, if you introduce more hyperparameter, right? It means that when you capture the coupling, there's a lot more variable that you introduce. Okay, so that will increase. So in our work, we actually use the sensitivity analysis. Some of the correlation coupling is not really important at all on the response, so we just take that off. But I didn't get your suggestion. You said we we want to do one model together, I didn't really follow that suggestion.
So like you have a different uncertain variables at different scale levels.
Yes, yes.
So I'm thinking that whether you can like consider all those uncertain variables at different fidelity levels together in one circuit model.
So I think then you're doing this. You have to couple all your different scale simulation together. Right now we try to decompose them. So we fit Metamodel to basically replace a single scale simulation. So we bring the up, one level up, another level up. So if you do it together as a one single model, then you will need to do coupled, multi-scale simulation again. That's just my direct, reaction to your suggestion, but I may get fully, what your suggestion.
Actually, it's not suggestion. I'm just thinking like, so that will help reduce the data set, like to calibrate the circuit model. Because at different levels, you need to build a lot of circuit models.
Yeah, right now we have two surrogate models basically. One is Macroscale, one is Mesoscale. And then those models are used in the Macroscale for simulations. But the dimensionality could be very high inputs when you introduce a lot of hyperparameters. Yeah. Mm-hmm.
So in many years ago, in another life, we were interested in this problem on coming up with a single representation of the uncertainty on both scales. Mm-hmm. And it comes out that these ideas of bi-orthogonal decompositions that usually people use to model things in space and time can be applied in space using two different resolution scales. So you can think one is the continuum, another one is the mesoscale, and then you actually produce sort of a KLE expansion that gives you eigenfunctions on the mesoscale and eigenfunctions on the continuum, and if you sample it, then you get microstructures that are actually properly correlated everywhere in the continuum.
Okay.
So you don't have to sort of put different things that are uncorrelated in different Gauss points.
Yeah. Okay. I would like to look at this. You said many years ago.
Yeah.
Okay. Yeah.
In another life.
Okay.
If there's no other question, let us thank our speaker.
Yeah. Okay. Thank you.